So if we try to draw a crude graph of an example of a Brownian motion, just imagine. So the first one says, if I take any interval, here's t plus s, and I generate many Brownian motions, and for every one I generate, I look at the difference between z at t and z at t plus s. So I fix t and t plus s, and I generate thousands of Brownian motions, thousands of these paths, random walk paths. And if I look at the difference between the z value, this is the difference in z. If I look at that difference between the z value at time t plus s and t, which could be positive or negative, of course, depending on which way the random walk goes, that value will be normally distributed, and it'll be a normal distribution. Delta z, what it's saying, is that delta z is normally distributed with a mean of 0 and a variance of s. Depends on the length of the interval. That's the third bullet. The fourth bullet says that if I have two intervals that are non-overlapping, so to change notation, I'll take the interval t to t plus s, and then the interval from t plus s to t plus s plus r. So here's another one. So now I'm fixing 3 points. And so I calculate a delta z as the difference over this interval, and then I calculate the second delta z as the change on this interval. So that height is, I'll call it delta z prime. So now what bullet 2 says is, bullet 3 says, is delta z is normal with a variance of s. Delta z prime is also normal with a variance of r. Right? That's what bullet 3 says. That both of these, if I fix these 3 points on the timeline, generate thousands of these random walks, and just measure the values of delta z and the values of delta z prime, bullet 3 says that they will both have a normal distribution. What the fourth bullet says is that, in fact, they're independent. Namely, that what does independent mean? Well, it's stronger than uncorrelated. Independent mean that if I look at the probability distribution of delta z prime, if I look at this as a joint probability distribution, this joint probability distribution is simply a probability distribution of the first one times a probability distribution of the second. Now, these three f's, of course, are not the same probability function. You may recall it's very common in statistics that one always calls the probability function f, but if it would help keep things straight, one can call this f1 and f2. These are three different probability functions, and independence means that the joint probability function of these two random variables is a product of the separate probability distributions, and of course each one of these is normal by the bullet 3. So we can think of Brownian motion in the same way that sums of binomial random variables approximate normal random variables. Time and time again, we've come to this notion that the binomial distribution is a good approximator for the models in finance. And here, once again, we're going to see the same thing, namely that we're going to see that we can approximate the Brownian motion change, a dz. We can approximate that with a binomial distribution. We know that a dz, a change from one point z to another point, is normally distributed, and we're going to approximate that with the binomial distribution. And this is a particularly good way of doing things when the interval of time is small, and that is ultimately our goal. So using the Brownian motion notation, dz can be thought of as the change in the value of a given process. It's a random variable because each process will give us a different value for dz. And it's the change over what might think of as an infinitesimal period of time, from the time t to, say, t plus delta t. Think of it as a small but discrete period of time. dz is, which is by definition the difference between z and these 2 points. We know, what do we know about dz? We know that it has a normal distribution and that the mean is 0 and the variance is the interval length. So we know that from the earlier properties.